Okay, so this is a two-dimensional vector addition problem. As always, you should attempt the problem before you watch the video so that you can check your work. With these vector addition problems, I like to make a simple diagram ahead of time, and that way I have some idea of what my resultant is going to be. So our first vector, we'll call the first vector A, and it's 23 miles in a direction 33 degrees north of west. Okay, so on my diagram here, we got northeast, south, and west. So 33 degrees north of west, we'll draw it like that. That'll be vector A, making an angle of 33 degrees. Vector B is 41 miles. Now it's telling me that it's 13 degrees west of south. I prefer to write that as 77 degrees south of west. And so vector B, I guess, looks like this. Right, making an angle of 77 degrees south of west. And it's pretty long, right? 41 miles instead of 23, so I drew it a little bit longer. And then vector C is 77 miles due east, like this. Vector C. Alright, so I'm guessing that my resultant vector, and you know, this isn't a perfect diagram or anything, and that's okay, but I'm expecting my resultant vector is going to have a positive x component and a negative y component, and the two will be fairly close to each other. Maybe less of a x component than a y component, we'll see. Alright, so vector C is 77 miles east. Alright, so whenever you're adding vectors in two dimensions, it's a three-step process. You break each vector down into components, you add up like components, and then you combine those components into a resultant vector magnitude and direction. So let's start off with vector A. Vector A on our coordinate system, vector A looks like this. And so it has an x component, ax, and a y component, and an angle here, 33 degrees. I'm going to go ahead and make the direction to the left negative, right? I'm going to use standard sign convention. North will be positive, east will be positive, south will be negative, and west will be negative. So that means that the x component of A is equal to the magnitude of A times cosine of 33 degrees. And it's negative, so that's minus 19.29. And the y component of A is positive, because it points up. It's 23 sine 33, which is 12.53 miles. Right? For vector B, let's see, vector B looks like this, points down like that. And you know, you can say that it makes 13-degree angle west of south, but I prefer to write it as a 77-degree angle south of west. So it has a x component bx and a y component by, and both the x and y component are going to be negative. Alright, so bx is minus 41 cosine 77. And this is why I like to measure my angles with respect to the horizontal axis whenever possible. That's because the x component is always dependent on cosine, and the y component is always dependent on sine. The more you're consistent about the way you solve problems, the less likely you are to make mistakes, in my experience. But if you wanted to, you could also say it's minus 41 sine 13. Either way, you get the same answer, 9.22. Right, so I could have said sine 13 here. By is minus 41 sine 77, or I could have said cosine 13, and that's minus 39.95. Now vector C, that just points east, so that's easy. Cx is 77, and Cy is 0. Okay, so the first step is done. We've broken each vector into components. Now we add up our like components. The x component of the resultant is is going to be minus 19.29 minus 9.22 plus 77, which is 48.49, and the y component of the resultant is positive 12.53 minus 39.95, so that's minus 27.42. Alright, so now I've combined my like components and I've got the components of my resultant vector. The last step is to make another triangle using the x component like this. So there's our x, which is 48.49, and the y component, which is a little bit shorter, so I was wrong in my original diagram up here, but I'm in the ballpark. And the y component is 27.42. That's our y. Now notice I didn't make the y component negative 27.42 because the fact that it's negative is indicated by the fact that it points down like this. This is just a triangle, so it's got sides of 48 and 27, and I need to find the hypotenuse. So the magnitude of the hypotenuse, I use the Pythagorean theorem for that. So that's 56 miles when I round off. And then to find this angle theta, I'll use the fact that tangent theta is equal to opposite over adjacent, and therefore theta is equal to the inverse tangent of opposite over adjacent, which is ry over rx. Okay, that's the inverse tangent of 27.42 over 48.49. And again, I'm not making either one of these numbers negative, so that's 29 degrees. And then this direction is east, and this direction is south, so we're going south of east. So the angle is 29 degrees south of east. Okay? Now, I didn't make the 27.42, the ry component, I didn't make that negative because my diagram already tells me that it's negative, and the fact that I'm going south of east incorporates that negative information in there. So if you try to take the tangent of a negative number in here, in the argument here, you make this negative, then your calculator is not going to know whether you mean that the angle is in the quadrant down here or the quadrant over here. And so you might get the wrong answer and get confused. So it's always safer to just use positive numbers here. So there's my final answer, and I'm done.